So in the last video, we started talking about equilibrium of a rigid body, and we did that by drawing the free body diagrams. But now we're actually going to look at solving what these support reactions are. Usually we're working with things like beams or other rigid bodies that we have reaction forces on, right? Support forces. So our reaction forces, usually if you have something like a pinned connection, right? We said that our reaction forces here are going to be in the y direction and the x direction, but there's no moment holding it in place. It's free to rotate. Or you could have a roller connection, right? So there's freedom to move in the x direction, but it's still supported by a normal type force in the y direction. Or we have a fixed connection where you're glued together. Something is glued together, or you're attached to a wall or something like that, where you have fixed supports in the x and y directions and a moment that prevents it from rotating. So there's no freedom of movement in any axis. So we're going to look at how we solve these equilibrium problems. And we do that with our equilibrium equations, very similar to how we did for equilibrium of a particle. But now, in addition to having the sum of our x forces equaling 0 and our y forces equaling 0, we're also going to have the sum of our moment equal 0. So we'll take the moment at some point and set that equal to 0. So the general procedure we use to go about doing these things is first we draw our free body diagram. Of course, that's always our first step. Then we're going to set up a moment equation. This is usually the easiest one to start with. You can start with any of these three, but usually it's easiest to set up a moment equation about some point where you have two unknown forces, because then you can solve for the other unknown force. Typically, you need at least three support reactions for something to be considered stable. In these problems, you'll often see three support reactions going on. So like a pin and a roller create an unknown y, an unknown y, and an unknown x. So usually we take the moment about something and solve this, and then we solve our x and y equations. But let's think about it conceptually, right? Let's take a look at an example here. So I have this rocket ship that weighs about 3.8 grams, and it's set up on top of this stack of erasers, and I've put a scale on the other side so that we can see how the reaction forces are working on this. So I want you to make a prediction. If I have a rocket ship that lands on the middle of this beam that weighs 3.8 grams, what are the support reactions going to be? So first things first, we would draw our free body diagram. I'll go ahead and draw out what we're seeing here. Right, and I'm going to use mass for this. Normally we would use force, but I'm just going to use mass for this example. And so I have I'm going to call this eraser in the y direction and my scale in the y direction. If I put a 3.8 gram weight on top of this beam, what is going to show up on the scale? What will the scale read? So we can see that the scale reads out 1.9. And this makes sense, right? We kind of expect this for each side to take on about half the weight of the 3.8 grams, right? If we think about just as a balance in general from our experience in the past, we could say, okay, well, the scale takes half the weight and the eraser takes the other half of the weight. But what if I move that rocket ship over to the far left side where the scale is? What will the reaction force at the scale be then? What if I move my rocket ship all the way over to the far right so that it's sitting mostly on top of the erasers? What are my reaction forces going to be then? So here we can see the eraser is taking on almost all of the weight of the object, while the scale gets almost none of the weight of the object. None of the force of the object is being seen on the scale. And we can prove that by taking a moment about the scale. Right, so if I were to move my 3.8 over to where it sits over here, and I were to take a moment about the scale, I would see that since EY and 3.8 are about the same distance away, my scale weight should be about 0. Of course, it's not perfect here because our wood does have weight in the real world, whereas in this example, we wouldn't calculate the weight of the beam, but we can see that if we take the moment here, our EY and our 3.8 have to be about equal because they're sitting in the same location. So our scale weight would be 0. Same as if we move it all the way over to the scale, and I were to take a moment about the erasers, right? When I move it all the way over to the far left, now all of the weight is centered over the scale, and the scale would be absorbing most of the 3.8 grams. We determine this using our y equilibrium equations and our moment equation. And so we can determine how much weight each one of these gets dependent on their distance from one of the other locations, right? By taking a moment, we can solve for one of the reactions and figure out exactly how much force each side is getting. How much force is the eraser side getting? How much force is the scale side getting? Right? So it's not always perfectly even unless you happen to be perfectly in the center. So as this weight moves around, your equilibrium will change. How much force each support reaction is getting is going to change. Let's take a look at some actual examples with the math. So this example asks us to find the support reactions for the beam. And this beam may look familiar because we've actually already drawn the free body diagram for this beam, right? When we were going through free body diagrams, we had this as one of our examples. So we already know step 1. We already know what the free body diagram looks like. So we'll go ahead and draw that again. I'm going to put this in blue here. Our free body diagram for this guy, right, is just drawing all of the applied forces we see. And then, of course, our reactions. So our reactions are at A. We have a fixed side at A and then a freestanding side on the left side. There's no support on the right-hand side. There's no support for this beam. All of the support is on the left side at A. And since it's a fixed support, it has a Y direction constraint, an X direction constraint or support, and then a moment. So these are the 3 reaction forces that we're going to have to solve for. They're all applied at A. I'm going to go ahead and I'm going to take the moment first, right? We typically take the moment first, but you can do the Y first, the X first. You're going to get the same answers, just that usually taking the moment first makes things a little simpler. You can solve things a little faster. So I'm going to take the moment. I'm going to take a clockwise moment, sum of the moments about point A equals 0, right? So when we set up our equilibrium equations, we always want to indicate what direction we're going as positive, right? You can pick whether you say up is positive, down is positive, counterclockwise, clockwise is positive. Whatever makes the math simplest for you, just make sure you're indicating so you know which direction you're marking as positive. Here I have the sum of my moments in the clockwise direction is 0. And if I go ahead and take all of my moments, so I'm taking my moments about A, I'm going to have this 1200 newtons times the distance away of 2 feet. That gives me the moment for that applied force. And it is positive in this case because I made clockwise positive and it's going positive clockwise around A. So I have that 1200 newtons times the 2 meters. And that's the only one for my applied force, right? Because about A, my Fy and my Fx both go through point A. So there's no moment for Fy or Fx. But we do include the applied moment at A, the reaction moment at A. So I would say plus M, plus the moment about A. So even though it is at that point A, it's included. Plus M. So I get my moment my reaction moment is 2,400 Newton meters, and my assumed direction was wrong. I had assumed that my M was going to be clockwise, right? I assumed this was clockwise, so I made it a positive clockwise in this equation here. But actually, when I did this math, I got M equals negative 1,200. My assumed direction is wrong. So when I write my answer, I'm going to put it in the proper direction, in the correct orientation. I'm going to say it's 2,400 Newton meters counterclockwise. We could have left it as the negative 2,400 clockwise, but it's a little clearer to go ahead and make it positive and just say, okay, this is going counterclockwise. The actual application is counterclockwise. We'll go ahead and do the other equilibrium equations, right? Our other equilibrium equations. Sum of forces in the x direction equals 0. And I'm going to make to the right be my positive. So to the right, the sum of forces in my x direction equals 0. And I only have one force here, right? I just have that reaction force at A. So that reaction force at A actually isn't there, right? Fx equals 0. There is no x reaction force. Now, we had to put it in there because it is fixed, and because if we did have some applied force later, where somebody comes and starts pushing on the side of the beam, then there would be an x reaction force. But in this case, it's just 0, right? There's no applied forces in the x direction, nothing causing there to be a support in the x direction. And finally, we'll look at our third equilibrium equation. Our last equilibrium equation in 2D is, I'm going to make up positive, summing our y direction forces equals 0. Right, so these are our three equilibrium equations. And we just go through and apply them to solve for these reactions. So Fy equals 0, and so I have a negative 1,200 applied force plus my Fy reaction. So I end up with my Fy is 1,200 Newton meters, and my assumed correction was correct, right? My assumed direction was up, and it is in fact going up. Right, I got a positive answer, so my assumed direction for that was correct. And those would be the three answers. Those are my three support reactions that I got from my three equilibrium equations. So what you want to do is draw your free body diagram, set up your equilibrium equations, and solve for the reaction. Typically three reactions, because that's what makes a system stable. Let's take a look at another example. Again, we have another example asking us to find the support reactions, but now we're finding them for the rocker at point A and for the pin at point B. So again, this is another one that we already did a free body diagram for, right? So if we look at that free body diagram again, where I have my beam here, I have the applied forces. I have this 200 Newton force that's applied, this 600 Newton force that's applied at an angle of 45 degrees. And then I have this 100 Newton force that's applied. And since it tells me that I have a rocker at A and a pin at B, I know what my support reactions are, right? I can look up the table in my book and I can say, okay, rockers are just like rollers where they only support in the Y direction. They have freedom to kind of rock back and forth in the X direction. So they have this freedom of movement in the X direction, and they have this freedom of rotation. So there's only, at A, I'm going to call this AY. So the support reaction at A in the Y direction. There's only an AY, no AX, and no moment about A for a rocker. And then at the pin, we know a pinned connection has a support in the Y direction and also in the X direction. I'm going to have a BX and BY support. So those in yellow, my AY, BY, and BX, are all of my support reactions that I'm going to be solving for. And this is how we laid out our free body diagram. And this is how we would lay it out if we hadn't done it before, right? So now we can use this to solve for our reactions. Now again, this is one of the times where it's easiest to start with a moment instead of starting with something like the sum of forces in the y direction. Because if I take the sum of forces in the y direction, I have two unknowns, right? AY and BY are both unknowns, so I wouldn't be able to solve anything if I started by taking my forces in the y direction equals 0. So I'm going to go ahead and start with a moment, and I'm going to take that moment about point B. You could take it anywhere about the beam. You could take it about point A if you wanted to, but notice that if I take a moment about point B here, and I'm going to go ahead and say counterclockwise is positive. If I take a moment about B here, then I don't have to include BX, BY, or that 200 Newton applied force. Instead, I'm only going to have the 600 Newton force, the 100 Newton force, and AY. Meaning that I'm going to be able to solve for AY, right? It's the only unknown in that equation. So if I set my equilibrium, my sum of my moments about B equals 0, I'm going to have, I'll do AY first. So AY is going clockwise, so it's actually going to be negative. Negative AY times the distance away, which is 7. Right, so that's, I'm just working left to right on this. So negative AY times 7. And then my next is this 600 Newton applied force. But notice that it's going in two directions, right? My 600 Newton applied force goes in this X direction and this Y direction that I'm going to have to split up, right? Because my Y direction has this distance here between point B, this 5 meter distance here. But notice that in our given diagram, my X component here of the 600 newtons also has a distance, this distance here, between where it's actually acting on the beam and where point B is sitting, where that pinned connection is actually sitting. It's 0.2 meters lower. So I'm going to have to include both the X and the Y components of my 600 Newton force, because it's not acting through the line of action of B. So for my Y component, I'm going to have this sine 45 times 600, right? This is our Y component here. And it's acting counterclockwise, so plus 600 sine 45, and then times that distance away, times that 5 meters. Times 5. I should have left a little more room. Times 5. 600 times 5 times sine 45. Scoot that in there. But I also want to include the X component, right? So my X guy is also acting, or no, is not also acting. It's acting clockwise. It's acting clockwise about point B, right? So it's going to be negative. Minus 600, and then the X component here is cosine 45, and times that distance, and that distance was given over here as 0.2 meters. 600 times cosine 45 times 0.2. Again, it's going clockwise, so that's going to be negative. And then the only other reaction we haven't accounted for yet, taken the moment of, is that 100 newtons. That 100 Newton force is going counterclockwise, so it's going to be positive. Plus 100 times its distance away from B is given here as 2 meters. Now essentially I can just punch all of that into my calculator and solve for AY, right? So just adding all the terms together, moving it over to the other side where the 0 is, and then dividing by 7. So when I punch all of this into my calculator, I'm going to get AY equals 319.5. 319.5 newtons. So that's our first reaction done. So now, like I said before, we had two unknowns in our equilibrium y equation, right? We had two unknowns. So if I were to do my sum of forces in the y direction, assuming up is positive, equals 0, I have negative 200 minus 100 minus 600 sine 45. And those are just all of the applied forces, right? Those are all the ones we know of. And then it's plus AY plus BY. Plus AY plus BY. But I know AY now, right? I just solved for AY. So since I know this AY is 319.5, I can plug all of this into my calculator and find what BY is, right? So when I plug and chug this, I get my BY reaction is about 404.8. 404.8 newtons. And so that only leaves me with one reaction force left, right? And this one we actually could have started with if we wanted to, right? We didn't necessarily have to do a moment first, because I can see when I look at my diagram, I only have two x forces, right? So when I take my sum of my forces in the x direction equals 0, I have the x component of my 600 Newton force, so 600 cosine 45, and then I have my bx pointing in the opposite direction of that, right? Minus bx. Minus bx. Right? And now I should have included on these ax and ay directional arrows. So my assumed directions were correct. So ay and by both act in the positive y direction. They both act upwards. And when I solve for bx here, I get bx is 424.3 newtons. But notice, this isn't actually like a positive number, right? The positive here means that my assumed direction was correct. So when I have this bx equals 424.3 newtons, it's actually acting to the left. Right, so I had assumed it was acting to the left because my 600 Newton one was acting to the right. Honestly, that is why I assumed that. So since I assumed correctly, I got a positive number, but note that it is actually pointing to the left. So it's very helpful to keep these marker arrows in your answers to know what direction it's actually pointing in, if your assumption was correct or if your assumption in your free body diagram was incorrect, and you need to kind of write that within your answers. So in this final example, it's asking us to find the support reactions at A, where again we have A is a fixed support, which we can tell because it's attached to a wall. Anytime you see kind of this like shaded wall that it's attached to, that's going to be a fixed support. We're finding the support reactions at the fixed support at A. So I can see here that I have a distributed load, right, my 0.5 kilonewtons per meter, a point applied load at the very end, the 3 kilonewtons, and then an applied moment also acting on the end, that 5 kilonewton meters. So go ahead and give this a shot before we work through this together. Try to work out if you can solve this problem using what we've learned in equilibrium reactions and our distributed loads and applied forces. So our first step is going to be the free body diagram, right? In our free body diagram here, we're going to go ahead and simplify those distributed loads. So I have these two kind of areas on here for this distributed load. I have this rectangular type load area, and then I also have a triangular type load area. So I'm going to treat each of those separately and find their own individual resultant forces for those distributed loads first while I'm doing this free body diagram. So my free body diagram here, this beam has kind of a curve to it. I'm just going to draw it as a line here because that curve doesn't really matter for what we're doing. But you can leave it. You can draw it in as the curved bottom as it has. And so what I'm going to have here is I have these two distributed loads. I'm just kind of dummy in so I can kind of see where they were. And I'm going to write in all of my applied loads. I'm going to put everything in the colors they were in. So this is that 3 kilonewtons. I had that applied moment around the end, 5 kilonewton meters. I have my support reactions at point A, right? And this is a fixed one, so I'm going to have a Y support, Y, an X support, AX, and then a moment supporting reaction. And that I'm going to go ahead and just call I'll call it MA. The moment support reaction at A. Again, you can name these things as they make sense to you. So, you could call them F, X, F, Y, and just M. Whatever convention you can use to keep them straight so you don't confuse them with the equilibrium equations themselves or another point along the beam. So here, if I look at this first area, right, this rectangular area distributed load, we know the distributed load is just the area under the curve, so my area of the rectangle is going to be that 0.5 kilonewtons per meter times the 6 meters, right, just the height times the length. So that 0.5 times 6 gives me 3 kilonewtons. 3 kilonewtons. And we know that for a rectangle, it acts halfway through the rectangle. That's where the centroid of the rectangle is. So that is 3 meters in. I'm going to put this resultant here, 3 kilonewtons, and it is acting 3 meters from A. So that takes care of my first one. And now I'll go ahead and look at my second one here, my triangular distributed load area, where my area is 1/2 base times height. So that'll be 1/2 times my base, my 3 meters, 1/2 times 3 meters times the 0.5 kilonewtons per meter. So when I plug that into my calculator, I get a resultant of 0.75 kilonewtons. Right, that's the area of that triangle. And for a triangle, the centroid of the triangle always acts 1/3 from the tallest side of the triangle. Right, so this acts 1/3 from this tallest side, so 1 meter. 1 meter in from the tall side, or 2 meters from the right. Think about it either way. If I draw that here in my diagram, I have 0.75 kilonewtons. And it is acting 2 meters away from the end of the bar. Or I can write it in as I have my 3 meters and then my 3 meters to where the shapes split. And then I have this 1 meter. Right, so in both of these cases, I have all 9 meters of this full bar written out. But now I have it broken down by where I have reactions at. So I've split things up in my free body diagram to make it easier for me. So let's apply our equilibrium equations now. I'll do a clockwise moment. Clockwise sum of moments And again, you can pick where you're going to take your moment about, but it's going to be easiest here to take a moment about A, right? Because then my A reactions go away, and all I'm going to have are the moments from my applied forces and the moment at A. So I can solve for the moment at A. So the sum of the forces about, or the sum of the moment about point A equals 0, that's our equilibrium equation, is going to be the moment about A, right? That's this force here, this reaction moment, plus our 3 kilonewton applied force times that distance, plus 3 kilonewtons times 3 meters, plus our next applied force is 0.75 kilonewtons times 7 meters, 0.75 times 7, plus our next applied force is 3 kilonewtons, 3 kilonewtons over the total 9 meters, 3 times 9, and then finally we have this applied moment at the end, right, which is going in the clockwise direction, so it's just going to be plus 5. Right, no distance on him because he's already in kilonewton meters. He's already a moment. So we just tack on that moment at the end. So when I solve this, I get that my moment at A is negative, right? Everything here was a positive, so my moment about A is a negative 46.25. So I had assumed the wrong direction, and it's actually acting counterclockwise. So my moment at A is 46.25 Newton meters counterclockwise. So that's our moments. Now we can go ahead and either do our f of x, our x component summation, or we can do our y component summation. Whichever way you do first is perfectly fine. You're going to get the same answers. So let's do our y one. I'm going to make up be positive. Sum of forces in the y direction equals 0. And then just finding all of those components, right? So my ay minus the 3 minus the 0.75 minus the other 3 kilonewtons. And those are all of my y reactions, right? Or all of my y applied forces. My moments don't go into consideration, my x doesn't. So I just get ay equals 6.75 kilonewtons. And I did assume the correct direction, so this is acting upwards. Right, ay is 6.75 kilonewtons acting upwards. And then I only have one equilibrium equation left and one unknown left, which, as we can see, it's the only x component on here, right? So again, much like our first example, our x component here is just 0. There's no reaction force in the x direction because there are no x forces being applied. 0 kilonewtons. So those are our reaction forces. These are how we go about solving them. Apply your moment equation and your two fx and fy. So very similar to how we did equilibrium of a particle. Now just always keep in mind to take a moment about some point along your beam, wherever you can get rid of the most unknowns.